This is segment 4 of the Module 8 lecture. In this section, we're going to review one example, example 1. And this is the example that we started this module with. So let's remember what this problem is about. So concerning today's health insurance is the amount of deductible that people with employer-provided health coverage pay. The Peterson Kaiser Health System Tracker claims that the average amount of deductible pay in 2015 is $1,077. So in a study, 78 individuals with employer-provided health coverage were selected at random to evaluate the amount of deductible they pay in 2016. The sample mean and the sample standard deviations from the 78 values reported is 1,168 and 369. Now, based on these sample results, we want to determine if at a significance level of 0.05, the true mean of deductible pay in 2016 is higher than the average amount paid in 2015. Now, you notice that I underlined different things on this problem. And the first one is the amount of deductible. That is telling you that that variable is a continuous random variable, because that's money. So it's a continuous random variable. Also, we're talking about the average amount. So we're talking about mu, the population average. I underline the significance level, 0.05, of the true mean. The true mean, that means mu, the mean of the actual mean of the population. And higher than is keying you into what is the alternative hypothesis. So when you read these problems, read them very carefully so that then you can summarize the information that is given to you. All right, in the next slide, I should say, the first step when solving this problem is summarize the information that is given to you, so that when you start following the 5 steps in finding the solution of this, of testing the hypothesis, you do not make any mistakes. So I strongly suggest that your very first step is summarize the information that is given in the problem. All right, so in this problem, we see that the mean that is assumed for 2015 is 1,077. And we're going to see if the mean in 2016 is the same as in 2015. So that's referring to this quantity. The sample size is 78 people were asked about how much the deductible they pay. The mean and the standard deviation of the amount paid by those 78 people is 1,168 and $369. And of course, the significance level is 0.05. All right, now that we have that information, we move on to the first step. So we need to define the hypothesis and the direction of the test. So as I said in the problem, they're saying we want to see if the mean on 2016 is higher than the mean in 2015, which is 1,077. So higher than, there is no equality in that statement. So they're telling you what the alternative hypothesis is. So the mean of the amount paid in 2016 is we're looking that it is bigger than 1,077. So the corresponding alternative hypothesis will be that the average either went down for the subsequent year or that remained the same. So that's the null hypothesis. And you remember that the alternative hypothesis determines the direction of the test. So here we're looking for values larger than 177. So this is a right tail test, and the significance level, as we said earlier, is 0.05. All right, so we have completed the translation of the practical problem into a statistical problem. All right, now the next steps is that of performing the statistical analysis. So number 1, we need to determine what distribution to use. So they're telling us that this is a random sample, so we know that we have independent observations. They don't say anything about the probability distribution of these amounts paid, but the sample size is bigger than is 78, which is bigger than 30. Then based on the central limit theorem, we can say that the sampling distribution of the mean is normal. Also, the population standard deviation is unknown, and we're going to replace it with the sample standard deviation. So all these three conditions tell us that we should be able to use the t-distribution with 77 degrees of freedom. So since we make the decision to use the t-distribution, then we know we're going to use the t-statistic or the t-test statistic. And then to calculate that statistic, we use the sample mean, which is 1,168, and we subtract the population mean under the null hypothesis, which is 1,077. We divide that difference by the sample standard deviation, and divide that by the square root of the sample size, which is 78. So when you carry out this operation, you see that the calculated value of the test statistic is 2.178. Right? Now we move on to the next step, which is setting the stage for making a decision. And again, in all these problems, I'm gonna illustrate both approaches, the critical value approach and the p-value approach. You do not have to use both. One is sufficient because they're equivalent, but I want you to learn how to use either method. So I'm gonna illustrate both. All right, so we're gonna use table 5 with a significance level of 0.05 and the 77 degrees to find the critical value. Now, when you look at your table and you look at the column where it says probability 0.05 and then you scan down, then you don't find the row for degrees of freedom of 77. But the closest value on the table is degrees of freedom of 75. So we're going to use that row. And then, so now you look at the row of 75 degrees of freedom, and then you look at the probability of 0.05, and at the intersection of those two, you find the critical value, which is 0.665. Remember, this is a right tail test, so it's the probability to the right of the t-value. That's what the table is giving you. Table 5 is giving you that value. So the critical value is 1.665, and then we know, because this is a right tail test, that the rejection region is going to be to the right of 1.665. All right. If you like to find the exact value of the critical value, you can use this formula in Excel, and you will find that the critical value, the exact value, is 1.66489. Very close to the value that we found on table 5. All right, so this is the critical value that defines the rejection region. All right, if you happen to decide to use the p-value approach, then again, we go on to table 5, and we're going to use a row of 75 degrees of freedom because that's the closest value. And then we look at that row of 75 degrees of freedom, and we're trying to find this value of 2.178. Of course, you're not going to find it. There's only a few values. Well, sometimes you may, but in this case, you don't find that value exactly. But you find that is between two t-values on that row, 1.992 and 2.377. So 1.992 is under the column for the probability of 0.025, and 2.377 is under the column for the probability of 0.01. Then that is telling you the p-value is between those two probabilities. But we don't know the exact p-value. We cannot determine it from table 5. So here is where the formula in Excel becomes very useful. And I'm giving the formula there, and if you put it into the Excel, then you will find that the p-value is 0.0163, as we say, between these two values. All right, so now we know the p-value and we know the critical value that determines where the rejection region. All right, so now we go on to step 5, which is we make a decision about the null hypothesis. So if we decide to follow the critical value approach, then you see that the t observed of 2.178, the calculated value of the test statistic, is larger than the critical value of that test statistic. That means that this value of 2.178 lies in the rejection region, and therefore we reject the null hypothesis that the mean is less than or equal to 1,077. If we decide to go with the p-value approach, you see that the p-value is 0.1623, which is smaller than alpha of 0.05. So for that reason, we reject the null hypothesis, because the p-value is less than alpha. So we reject the null hypothesis that the mean paid in 2016 is less than or equal to 1,077. So we reject that. So once you reach this statistical conclusion of whether to reject or not reject the null hypothesis, you need to interpret that decision. So the interpretation of our statistical decision, now we're going to translate it into the practical conclusion. And then we say that the actual average amount of deductible that people with employer-provided health coverage pay in 2016 is higher than the amount paid in 2015 at a significance level of 0.05. So again, our conclusion is that the amount paid in 2016 is larger than the amount paid in 2015. Now, if someone says, well, how much more did we pay in 2016? Well, we don't know. We just know that it's higher. And this is where you could use the confidence interval to provide a range of values where you think that the actual mean would be. So the confidence interval complements, or supplements, if you will, the hypothesis test. All right, I'm going to stop here. This is the first example. In the next recording, I'm going to review other examples.